Hello, I'm Johann Graf Lambsdorff, and I would like to tell you today something about the Phillips curve. And let me start right away with one standard variant for the Phillips curve. It's a relationship between inflation pi, and this is this year's inflation, and inflation corresponds then to the level of inflation we had last year, so this is pi minus 1, plus some parameter gamma times the output gap, and I denote this by y tilde. We define the output gap by y tilde being equal to aggregate demand y minus potential production y dash over y dash. The logic is potential production. That's the level of production we would get if all resources, humans, people, and capacities, machines, if they are adequately utilized. So there is no excessive unemployment, no idle resources. And when demand is equal to this level, inflation will stay constant. There is no upward pressure on inflation. But if demand is in excess, maybe let's say 2% above the potential level, then these 2% will push upward inflation by the parameter gamma, and this gamma is the inverse of the price elasticity of demand. So this is one version of the Phillips curve that is quite often found in the literature, and one method for deriving this builds on limited information, and more recently there is more research into limits on rationality and how such limits of rationality might imply this type of a Phillips curve. Now, this is not the only Phillips curve that we know. There is another variant that is built upon the idea of rigidities. Rigidities in the sense that producers cannot always adjust prices as they like. They sometimes have to leave prices unchanged. And in such a case, one can then derive a different type of Phillips curve, which is known as the new Keynesian Phillips curve. Okay, but today we have a closer look at how limited rationality induces this type of a Phillips curve. And we do this by help of a classEx game. If you are a lecturer or a student, you should definitely play this game in order to fully understand the logic. Now, let me read out the instructions to you. Each participant is in the role of a producer who can make a profit by choosing the price P appropriately. Now, I have to tell you one thing. We played the game half a year ago with 500 students at once. So it was in a huge online meeting, and all these 500 played the game simultaneously. They were all in the same role as a producer. And as you can read, the demand for each producer is y minus omega, y equal to omega minus p. So they choose the price, and automatically the demand is then determined by this function. So the lower the price chosen, the higher the demand y. And demand increases also with the exogenous influence omega, which indicates the maximum possible demand at a price p equal to 0. And each participant automatically produces a quantity equal to the demand. Let me illustrate this curve. This is the price P. This is the quantity Y, and demand is given by this downward sloping curve, which has a slope of -1. Now there are costs to production. The capital P is the average of prices chosen by all participants. Now you see why it is relevant to play this with a huge crowd of people, because this term now introduces an interaction between the participants. So the capital P determines the costs and is necessarily unknown at the beginning of a round. The unit costs are capital P minus 10. So here, these are the costs, and they are the capital P minus 10. So the costs for the entire production are then the Y, which is the quantity produced, times the unit cost, capital P minus 10. Okay, and this game is then played across 12 rounds. In the first round, the omega amounts to 30, such that this denotes then this point here, the 30, and also this point, that's both 30. And from round 7 to 12, the omega is increased to 50, such that the demand curve shifts upward. When we played it, we selected a variety of participants to actually receive the money they earned afterwards, so there was a real incentive to maximize. And what will people now do when they maximize? Well, let's talk about profit. Profit. The profit is equal to the quantity times the price, which is the revenue, and then subtract the cost, which is the quantity Y times the unit cost, capital P minus 10. And when we insert for demand, we see this is omega minus P times P minus omega minus P times capital P minus 10. And since students are incentivized to maximize, they should take the first derivative of this. Or maybe just intuitively, they might have some idea about maximization without actually doing the calculation. So what they will do then, the first derivative, that's the omega here, minus, now this is basically P squared, minus P squared. So derivative is minus 2P. And the first derivative of this here, well, basically the omega and all this, that's a constant. So we can forget about the omega here, but here we have them minus P, minus P, that jointly makes it plus this constant we have thereafter, the capital P minus 10. And for a profit maximum, this must be equal to 0. We can rearrange this, bring the 2P on the right-hand side, divide by 2, and all together we end up with P equal to omega plus capital P minus 10 over 2. That is an intuitive logic. it tells us that prices are strategic complements. You can maybe understand the logic by imagining why the costs are determined by this capital P. Just imagine that each producer supplies the product to all the other ones. So each producer also receives from all the other ones their production as an input for one's own production. In such a case, all these inputs from the others are priced according to their price, to the price that they set. Now, if they determine a high price on average, one is then forced to add on, to mark up on these costs by increasing also one's own price. So that's a reasonable logic why prices also in reality are strategic complements, positively depend on each other. And what you see here can also be illustrated here by denoting the profit maximum here. Imagine for a moment that we fix a price of 15. In such a case, the quantity produced is also 15. So this is the quantity, and this here is the profit per unit. And the total profit is equal to this rectangle. Now assume for a moment that we had taken a rather low price. In such a case, the rectangle would be quite flat. And in fact, it is easy to imagine that such a flat rectangle is not the optimum choice. Sort of the total area covered by the rectangle is then rather minor. Or assume that we take a price that is extremely high, then we have a rectangle that is rather flat here. And again, this would not be optimal. Rather, the optimal shape for the rectangle is to be a quadratic form. So it should look like, maybe like this. Okay? Now if you observe that the capital P increases, that the costs increase, then we are pushing upward also the price, because otherwise the rectangle would become sort of flat. It would be too flat. So one must increase halfway also by one's own price. So that's the logic here. And we do observe that students somehow have a sense of this logic. In our data, we do observe that they do react positively to the average price chosen by others. However, there's one thing where they had really difficulties with, and that was sort of finding the equilibrium. Because the equilibrium requires symmetry. Symmetry means all have the same instructions. They are all reading the same instructions, and equilibrium now assumes rationality. It assumes that all find the rational solution. Thus, they are all equal. And the consequence then is that the P chosen by one producer must be equal to the prices chosen by all the others, and then equal to the capital P. And when we recognize this, we can simply insert this into this function here. So we have here minus 2p plus capital P. So we can simply erase this minus 2 with this here. So we are left over only with minus p. And this provides us with a simple solution. The p must then be equal to omega minus 10. And when we insert this into the demand function, the demand is y is equal to omega minus p. And inserting now for the p, you observe that the y, the production, should be equal to 10. So rationality requires people to set prices such that the quantity is constant. Now, this here. This is the solution. A vertical line for production. And that is somehow surprising, because when one has a first look at the game, at the increase of demand, one is tempted to believe that the quantity produced will increase with the omega, but this is not so. And the reason is because the increased omega translates to higher prices, but then also translates to higher costs. And the higher costs translate again into higher prices. And the higher prices induce again higher costs. And all this overall induces that prices increase to such an extent that there is no reaction to quantities. So whatever level of omega we choose, we would pick only a point on this curve, on this line. And this corresponds to what we call the long run Phillips curve. Phillips curve. In the long run, demand does not drive up production. It only impacts prices. That's the idea. However, is that also what people fully understand and what they immediately do when they play the game? No, it is not. Here, I tell you about the data that we found. Data with our 500 students here in Passau across the 12 rounds. And so here is round 6 and this is round 7. They are the ones that are of utmost interest. 8, 9, 10, 11, 1, 2, 3, 4, 5. Okay? Now I plot here the prices and the quantities on a scale from 0 to 40. Okay. Now our equilibrium predictions would be that the quantity should always be equal to 10. And prices should be, no, take another color to have a nice one. Maybe this yellow, is that good? No, that's not so good. Let's stick with the blue. So the prices should be equal to 20 because the omega is 30 in the beginning, 30 minus 10, so that's the 20. And then suddenly the omega increases to 50. 50 minus 10 is 40. So we should get an immediate jump in the price level to the higher level. So that's the equilibrium prediction in line with the long-run Phillips curve. Now, what did we find? Basically, the prices, well, there was some heterogeneity with this, but basically it was somewhere around 20. But then it did not jump all the way to the 40. Rather, the jump was milder, only to 30. And then it took some time to converge to the 40. Now, what's happening when one does not fully increase the price? Well, in such a case, certainly the omega is then at 50, the price only at 30, such that demand is not at the equilibrium level of 10, but rather above. It indeed, after some initial time with some heterogeneity here, it then increased to 20, and then over time it came down again to the long-run equilibrium. So that is a fascinating finding, because this is what we call the short-term Phillips curve, and that we can relate to this function. What is the reason for that? Well, the most likely reason is sort of just have a look at this function. And participants don't perfectly apply this function and the corresponding logic for symmetry. Rather, they form some expectations with respect to the capital P. So they don't infer the average price from the model, from rationality, from logic, but rather they form some expectations where they do something else. They form, well, expectations with a sense of inertia. And an easy way to capture this would be to assume that they expect unit costs, and therefore the average price, to be equal to what they observed in the previous round. So this is then a term where some sluggishness enters, some inertia. When you apply this logic, then you quickly observe that this sort of development emerges, because in round 6, average price was 20. Now, inserting this here means we have the 20 minus 10, and in round 7, we have then the omega of 50. Okay, so 50 plus 20 is 70, minus 10 is 60, over 2 is 30. And that's exactly what we found here. Participants picked a price of 30. Now, what's going on in their minds? Well, basically, we have two explanations. The first one is limited information, and that's the classical approach to understanding this Phillips curve. The point is, in the 1970s, this has been advanced by Lucas and Phelps to highly reputable economists who thought about maybe limited information can explain that. People just don't know how the unit costs are determined. This is a black box to them. And since they have no idea of where these unit costs come from, sort of the prices of all the others, they are not directly observable. They are sort of surprised by these prices. And when this is so, they take them as given, and one idea would be they just look to what they experienced in the past. Now, this is not an explanation for the behavior in our game, because there is no limited information in the game. People, participants, know how this average P is formed. They would have the capacity to infer the equilibrium, but they just don't do it. And that points to limits of rationality. They don't reason all the way through to come up with the equilibrium, but they get stuck somewhere in between. So think of the following. If you were smart, what would you do? You would then know that all the others take a price of 30. Now, if they take a price of 30, then you would insert the 30 here, because you anticipated that. What do we have then for round 7, for you as a smart one? We have the 50 plus the 30, makes it 80, minus 10 is 70, over 2 is 35. So, what you would do as a smart person, you would take a price above, here. Now let's assume that you are so smart to do this, but all the other ones do so as well. Well, in that case, you should recognize that all the other ones are so smart to take a price of 35. Then you insert the 35 here, and then you end up with a price of 37.50. You should go here. And again, if you believe all the other ones are so smart, then you should go here, 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 and so forth. But it requires infinite steps of reasoning to make it all the way to the equilibrium. And you must form higher order beliefs such that you anticipate what all the others do, and anticipate that they anticipate, and so on. That they form all these higher order beliefs such that you can sort of anticipate with infinite steps of reasoning the actual equilibrium. And here is the point where we know that people just don't do that. Infinite levels of reasoning, no chance. And in fact, our data even points to the idea that people carry out only one single step of reasoning. Basically, they take just the price here from the past. Okay. Now, we still have not derived this form of the Phillips curve here, but we can extend the model a little. Let us assume for a moment that the omega does not jump from round 6 to round 7, but rather that the omega develops steadily over time. So demand shifts each round a little. In such a case, it might be reasonable to assume a slightly more complex function for the formation of expectations. And this would be to assume not that the price will be, the average price, capital P, will be identical to the past, but rather that inflation will stay constant. And inflation, we can write this as the expected capital P over the previous round's price. That should be equal to the previous round's price over the one before. So the ratio should stay constant. If we had here sort of 10% inflation, then this amounts to 1.1. And then we expect the same to happen this round again. Now, once we have this, we can rearrange to see that the expected capital P will be equal to P minus 1 squared over P minus 2. Okay? I just multiplied with the denominator here. And once we insert this here, you see, well, I multiply with a 2, so I have 2p, should be equal to omega plus, now I insert here for the expected capital P, P minus 1 squared over P minus 2. Yeah, and then the rest is the minus 10. And now I apply a minor trick. I take away one of the p's here, bring it to the other side, such that I have minus p here. Okay? And then we are almost done, because we just divide by p minus 1 on both sides, such that we get p over p minus 1 should be equal to, then this term only becomes p minus 1 over p minus 2 plus omega minus 10 minus p over p minus 1. Okay? And now you should see that this is inflation, as we have it here. This is inflation, or sort of it corresponds to it. It's not perfectly like that. We would still have to subtract minus 1 from both sides to come up with the actual definition of inflation, which is basically p minus 1 over p minus 1. And we can get there by subtracting here minus 1 and here minus 1, and then sort of expanding this minus 1 as p minus 1 over p minus 1. So I hope you are with me, even if this gets a little sloppy. So this is then p minus 1. This is the pi. This is the pi here. This is pi minus 1 here. And this, well, what's this? This is y minus 10. Because here's the omega minus the p, that's production y. Okay? And the minus 10, now this corresponds to potential production. This is the long term, the natural rate. So ultimately we come up with this equation. What is still missing here is the gamma. And here, just believe me, just trust me, this gamma can also be derived in particular for a demand function that does not have this slope of minus 1. It could have any other slope. And what we then observe is that this gamma corresponds to the inverse of the price elasticity of demand. So now you have seen how this Phillips curve can be observed in a classroom setting by help of a game, and how limited rationality contributes to this short-term quantity reaction. I thank you for your attention.